Hello everyone, I'm Norman Wahlberger, and this is the second video where we're talking about multiplicative functions and Dirichlet series via box arithmetic. So today we're going to look at a particular kind of construction that occurs in analytic number theory called the Dirichlet series. Here's a general form of a Dirichlet series. Eta of S, it's generally regarded that S is a complex variable, a complex number variable. It's a sum from n equals 1 to infinity of a sub n over n to the s. So a sub n is some prior sequence. So we have some sequence a sub n, and we're summing these sort of weighted reciprocals of powers. Now, it turns out that these kinds of series form in some sense an algebra under a certain type of product or convolution. And the core example of such a thing, sort of the motivating one, is the Riemann zeta function, where the sequence a sub n is just constant sequence 1. So most undergraduates will probably not have touched base with this too much unless they've taken sort of specialized courses in analytic number theory. But I want to sort of reposition this topic as a sort of elementary aspect of box arithmetic. So I think that what's really happening here is in some sense very general and sort of fundamental at a certain level. And it will also give us a chance to reposition our thinking a little bit about how we think about polynomials, and so, what kind of operations we apply in arithmetic and how we apply them. So lots to think about in this lecture. But before I go there, let me just give my usual reservations about this kind of thing. So right, from my point of view, this is all in quotes because, first of all, it doesn't make sense in general to take a natural number and raise it to a general complex number. That doesn't mean anything to me, or it doesn't mean anything precise. If n is 5 and s is 9 over 7 plus 4 over 3i, what does it mean to raise 5 to that complex power? I mean, if you actually ask what exactly do you get, then you typically only receive some ambiguous answer from the analysts or the number theorists. And so that sort of renders this thing sort of necessarily not a proper function. So we're almost immediately dealing with something which doesn't really make sense. And then when we attempt to sort of add up all of these things or extend our arithmetic from the finite sums and finite products and so on that we're used to some kind of, infinite domain, as suggested by this, then we're just magnifying those problems. So one of the aims here is to find some alternative way of thinking about arithmetic so that we don't have to always be invoking these essentially nonsensical appeals to doing an infinite number of things. Right? We want to reinterpret the current understanding so that it can be expressed in a way that a computer can understand and work with explicitly, concretely. So one of the interesting and appealing aspects of box arithmetic is that there's sort of this natural layering of things, sort of a natural way of going from one step to the next step lower down, which is more complicated. So that involves the objects that we're talking about, like zeros and natural numbers and polynumbers and multi-numbers, etc. But also includes the operations, starting with addition, then multiplication, then the caret operation, and further products that we haven't talked much at all about. So today, the caret operation is going to play an important role. We want to bring that forward a little bit and emphasize that this is not some obscure kind of thing. It's actually really very important for fundamental arithmetic, but also for applications to number theory. Okay, so let me just review some things and let's introduce a slight variant to things that we already know about. So we know that a natural number is a box of zeros. Zero is just an empty box. There's a zero, there's a zero. Now here's a box with 2 zeros in it. That's what we think of as being the number 2. Here's a box with 1 zero in it. That's what we think of as being the number 1. Okay, that's very familiar, I hope. Let's introduce a slight variant of that, which is particularly useful when we are thinking about the caret operation. Nat star. So a natural star number, this is a new definition, and whether it should be like this or maybe natural to the star, okay, I won't fuss around too much about what the actual terminology is. We'll just loosely talk about it this way for now. What this thing is a non-empty box of zeros. So when we're talking about natural numbers, this thing here qualifies as a natural number because it's a box of zeros, which happens to be empty. When we go to nat star, we want to exclude the zero, okay? So we want to start counting from 1. 1, 2, 3. Here we're counting from 0. 1, 0, 1, 2, 3. So in mathematics, there's this dichotomy about whether in a given situation you should start counting with 0 or start counting with 1. And in different situations, either of those could be maybe more apt, more convenient. What we're doing here is just introducing some alternate notation so that in those cases where it's more convenient to count starting with 1, that we have some pre-existing notation for that. Okay, so that's nat star. And then when we go down a level to poly, I remind you that a poly is a box of natural numbers in this sense here. So let's define poly star to be a box of natural star numbers. So a poly star is like a poly, except that when you look inside the box at the natural numbers that are appearing in there, you don't find any zeros. Okay, so that's a poly star. Okay, so let's have a look at poly star. All right, these are poly numbers that don't have any zeros inside them. So here's A and here's B. These are both poly star numbers. It's a box of natural numbers. You recognize this is the natural number 1. This is the natural number 1. This is the natural number 3. Here's the natural number 1. Here's the natural number 2. So these are both boxes of natural numbers, but they're natural star numbers because they're not zeros. There are no zeros in these boxes. In other words, there are no empty boxes by themselves as elements. So let me just remind you about the basic 3 operations. Addition is just dumping all the entries into a new box. So A plus B is just this thing here, the obvious fashion. A times B, the way we get that is we form all possible combinations of an element in A and an element in B, and we add those 2 elements. So if we add this and this, we get this. 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 And this and this, we get this. Okay, so that's the product of these 2 boxes. And then we have the caret operation. Okay, so the caret of 2 boxes is the box you get by taking elements in A and elements in B and now multiplying them. Okay, multiplying them, not adding them as we did for the multiplication. So this times this, well, this is 1 and this is 1, so 1 times 1 is 1, and 1 times 2 is 2, and 1 times 1 is 1, and 1 times 2 is 2, and 3 times 1 is 3, and 3 times 2 is 6. So there is the caret of A and B. And let's just remind ourselves that we have a kind of distributive property. First of all, both these properties are commutative, and both of them are associative. But what about distributivity? Well, both of them are distributive with respect to addition. So A times B plus C is A times B plus A times C. And also, A caret B plus C equals A caret B plus A caret C. So, in terms of doing algebra, we might say, okay, in this domain of just polystars, we could look at the familiar operations of addition and multiplication, and that would give us the usual polynomial algebra that we've been thinking about since at least high school. But we could also do something that we're much less familiar with. We could look at an algebra formed by considering addition and the caret operation, because the caret operation and the addition are related in this nice way via this distributive law. And we have commutativity and associativity of both operations. So, that's a very natural thing to think about. What happens? What does that look like? that sort of algebra structure. All right, so we can ask ourselves, what does this plus caret algebra of polystar look like? But before we do that, let me answer a natural question, which is why are we considering polystar instead of just poly? Because after all, the caret operation works on polys just as well as it does on polystars. Well, here's the answer. Suppose you have this poly times this poly, okay? The way we multiply them is we just take all possible sums. So 0 plus 0 is 0, 0 plus 2 is 2, 1 plus 0 is 1, and 1 plus 2 is 3, and 3 plus 0 is 3, and 3 plus 2 is 5. Fine. And now suppose we look at the caret of these two things. So now we have to multiply things. So 0 times 0 is 0. 0 times 2 is 0. 1 times 0 is 0. 1 times 2 is 2. 3 times 0 is 0. And 3 times 2 is 6. Well, we see that these two zeros here, because we're doing a lot of multiplications, mean that we're getting a lot more zeros at the next stage. And if we took this thing here and multiplied it by some other poly with a 0 in it, then the result would have even more zeros. So these zeros kind of reproduce like rabbits, you know, and it's not so interesting. It's just not so interesting. So it's for that reason that we're going to restrict ourselves in this little world here just to polystars, so that all our poly numbers start with ones, if anything. There's no zeros. So for example, let's do a bit of arithmetic here. Let's take the polystar 1, 2, 3 and caret it with itself. So we look at all possible products. 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. We get this box here. And we could a little bit more efficiently describe that by not repeating all of the repetitions, but just recording how many of each of things there are. So there's 1, 1, so we don't need to say anything, but there's 2, 2. So beside the 2, we'll put a little 2 to the left. Okay, it means sort of like 2 of them. And there's 2 3s, so we'll put a little 2 to the left and below the 3. There's 1 4, there's 1 6, and there's 1 9. So this is a little bit more efficient way of describing that same result. Now, if we were going to go down this road, we could be a little bit more efficient. So what we're really doing here is recording the various multiplicities that the various possible natural numbers that are allowed, namely 1, 2, 3, 4, etc., are appearing with. Okay? So another way of doing this a bit more systematically is to just list all the natural numbers from 1 to 9 in this case, and record for each one of them the multiplicity that we're getting with this thing here. So there's 1 1, there's 2 2s, there's 2 3s, there's 1 4, there's 0 5s, there's 1 6, there's 0 7s, there's 0 8s, there's 1 9. And when we do that, we see that essentially another way of thinking about this box is in terms of this list of multiplicities. Okay? It's a list now because it's ordered, because we're using the fact that our natural numbers are naturally ordered, starting with 1 in this case, our natural star numbers, 1, 2, 3, 4, etc. So it makes sense to just record the multiplicities, right? We don't really need to repeat these numbers here. We know what they are by their positions. So we just record 1, 2, 2, 1, 0, 1, 0, 0, 1. And from this, if we wanted to know what the multiplicity of 5 is, we go 1, 2, 3, 4, 5. There's 0 5s. And how many 6s are there? 1, 2, 3, 4, 5, 6. There's 1 6, etc. Okay, so this is actually quite an important thing, that we have a multiset on one hand. So this multiset here, which is unordered, has repetitions, can be alternately encoded by a multiplicity list, which is now a list in the sense that it's ordered. And repetitions are allowed, so this accords with our general LOMS lists, ordered sets, multisets, sets sort of notation. We're using square brackets to denote lists like a computer scientist would. Okay, so a little bit more formally now, let's officially introduce the idea of the multiplicity list, or M-list, of a polystar. So the multiplicity list, or M-list, of the polystar P. So here it is written in the form where we're recording the number of ones. So there's A1 ones, there's A2 twos, there's A3 threes, all the way up to, say, A sub k k's. This is a polystar because there are no zeros. Okay, so that's a box. It's an unordered collection where repetitions are allowed. And now what we're going to do is introduce this other data structure, which is a list, where we just record the numbers or the multiplicities of all of the natural numbers in order, 1, 2, 3, all the way up to wherever we're going. So we record A1, A2, A3, all the way up to AK. Let's call that M of P, the multiplicity list of P. P is a polystar. This is something a little bit different, although it's pretty well equivalent to this, right? But it's in the form of a list, or equivalently a vector. Pretty well the same thing. So the entries here are going to be, well, in this case, natural numbers, but including 0, right? So it's certainly possible for the number of 3's to be 0. So this thing's going to have zeros in it. This thing doesn't have zeros. And it's also usual to sort of allow this convention to be flexible about the end. You know, so, I mean, if the last entry here happened to be 0, well, you know, we could in principle get rid of that. So we'll allow ourselves to append zeros or remove zeros at the end and regard those things as being equal. That makes the addition operation on polystars sort of transferable to the vector world, right? Where if you allow the vectors sort of to have more entries, if we're adding a vector with 5 entries and a vector with 7 entries, we just think of padding that vector with 5 entries with 2 additional zeros, and then they have the same size, and then we just add component-wise. Okay, so now let's introduce what we call the caret convolution of M-lists. What we're going to do here is we're going to transfer the caret operation, which is on polystars, to a corresponding operation on the associated multiplicity lists. So there's a correspondence between these polystars and these multiplicity lists. If we know the polystar, we know the multiplicity list. If we know the multiplicity list, then we can recover the polystar. So they're completely equivalent. But over here in the polystar world, we have this operation of caret. Okay, so we can just define the operation over here in the world of lists or vectors to be the corresponding thing. Okay, so formally, if P, Q, and R are polystars, let's say with P caret Q equals R, then we'll define M of P convolution M of Q to be M of R. Here's the multiplicity list of P, here's the multiplicity list of Q. We're going to define this operation to be what it has to be in order to get M of R, so that the convolution here exactly corresponds with the caret operation in the world of polystars. So let's see what this looks like. So here is a polystar, 1, 1, 3. Here's another polystar, 1, 2, 2. And we're going to caret them. That means take all possible products. So 1 times 1 is 1. 1 times 2 is 2. 1 times 2 is 2. 1 times 1 is 2, 1. 1 times 2 is 2. 1 times 2 is 2. 3 times 1 is 3. 3 times 2 is 6. 3 times 2 is 6. Okay. In terms of multiplicities, so another way of sort of thinking about this is to record the multiplicities that the various numbers involved come with. So the numbers involved here are from the range 1 to 3. So we can record this thing as being 2 1s, 0 2s, and 1 3. We can record this thing as being a single 1, 2 2s, and 0 3s. And over here, we guess we have 2 1s, 1, 2, 3, 4, 4 2s, a single 3, there's no 4s, there's no 5s, and there's 2 6s. Okay, so at the level of the multiplicity lists, the multiplicity list for this would be 2, 0, 1. The multiplicity list for this is 1, 2, 0. Okay, but that 0 at the end, we've agreed, it's not really necessary, so it's the same as just 1, 2. So according to this definition, the convolution of this M list and this M list should be the multiplicity list for this thing, which is 2, 4, 1, 0, 0, 2. All right, so we've defined an algebraic structure essentially on vectors, coming from the fact that we can identify these vectors with polystars, and over in the polystar world we have the caret operation. So we're just bringing the caret operation into the world of vectors where it's a little bit less familiar. So let's see what's actually involved. So maybe I'll do it at this stage here. So let's say we had to find the caret of these two things, right? So how many 1s are going to be in the result? Well, how do you get a 1? We're talking about taking an element here and an element in here and multiplying them. So 1 times 1 is 1. So that's the only way we're going to get a 1 over on this side. And how many 1s are there here? Well, there's 2 of them. And how many 1s are there here? Well, there's 1 of them. So how many possible products are we going to be able to make that result in a 1 over here? Well, there's 2 of them here. There's 1 over there. So we can do this one times this one, or this one times this one. There's 2 times 1, which is 2 possible ways of getting that. How about 2? How can we get to 2? We can get 2 by multiplying 1 by 2 or 2 by 1. So this combination here, 1 times 2, we can do that in 2 times 2 possible ways. Okay? Multiplicity here is 2, the multiplicity here is 2. There's 2 choices here, there's 2 choices here. So the possible ways of pairing them up is 2 times 2, that's 4. And the other way was 2, 1. Well, there's 0 2s over here and only 1, so there's no way of getting a 2 from that combination. So this 2 is being obtained with multiplicity 4, and that's because that 4 is coming from the product of this multiplicity 2 with this multiplicity 2. So we can go through the elements. Let me do the 6, okay? How can we get a 6? Well, so you can get a 6 by either multiplying a 2 on over here times a 3 over here, but there's no ways of doing that. Or by multiplying a 3 over here with a 2 over here, and there's 1 times 2 equals 2 ways of doing that. So that's what this caret convolution sort of looks like at the level of the actual M lists or vectors or multiplicity lists. Okay, so let's have a look at another example to get us used to how this caret convolution works at the level of these multiplicity lists. So here's a multiplicity list, 2, 1, 3, and here's another one, 0, 1, 4, and we're taking the caret convolution of them. And I'm claiming that we get this multiplicity list. Okay, so to try to explain that, let's just step back one step and convert it again just to boxes. So this is the multiplicity list of an M set, which has 1s, 2s, and 3s. And there are 2 1s, 1, 2, and 3 3s. This one here is an M set with 0 1s, 1 2, and 4 3s. Okay, so when we take the caret of those two things, we can get any number from 1 up to 9, all possible products. Okay, so how are we going to get a 1? Only by taking a 1 here and multiplying it by a 1 here. But there are 2 of these over here, and there are 0 over there. So there's no such product that will contribute to a 1 there. So that's going to be 0, which is the product of this 2 and that 0. How about 2? We can get a product of 2 by taking a 1 times a 2 or a 2 times a 1. If we take a 1 times a 2, there's 2 1s over here and 1 2 over here. So there's 2 ways actually of doing that product. 1 times 2 or the other 1 times 2. So there's 2 2's coming from that combination. And there's also the possibility of a 2 times a 1. But there's 0 1s on there. So 1 times 0 is 0. So there's a total of 2 ways there. How about 3? How can we get 3? We can get 3 by taking a 1 here and a 3 there, and there's 2 times 4 ways of doing that. So there's 8 possible ways, because the other way, a 3 and a 1 is not possible because there aren't any 1s. How about a 4? We can get a 4 only by multiplying 2 by 2, and there's a 1 times 1 way of doing that. There's no way of getting a 5 as a product. How about 6? We can get 6 by multiplying a 2 times a 3, and there's 1 times 4 ways of doing that, so 4 ways of doing that. Or by multiplying a 3 over here times a 2 over there, and there's 3 times 1, 3 ways of doing that, for a total of 7 ways of getting 6. Can't get a 7, can't get an 8, and to get a 9, we have to take a 3 times a 3, and there's 3 times 4 ways, 12. So then we run through the multiplicity list, and here it is right there, 0, 2, 8, 1, 0, 7, 0, 0, 12. Okay, what's the general rule? Just at the level of multiplicity lists, we have one sequence, AN, just the elements in the list, starting from 1. A1, A2, A3, etc., up to some A sub k. And then in the second one, we have B sub 1, B sub 2, up to B sub L. So when we're convolving them, we're going to get another sequence as a result, C sub 1, C sub 2, up to, well, the maximum possible is K times L, because that's the maximum possible product that you're going to be able to get. And what is this Cn in terms of the A's and the B's? Here's the critical formula. The mth one, so C sub m, is obtained by asking, well, how can we get an m? How can we get an m? Well, we can get an m by choosing any two numbers that multiply to m. Okay, so any two factors that multiply to m, and seeing how many of them there are on this side and on this side, and multiplying those multiplicities. So if there are, say, a sub I, i's, and b sub j, j's, and I times j equals m, then we're going to get a contribution from those, which is just the product of ai times bj. But we have to sum over all possible ways of writing that m as a product of I times j. That's what we've been doing here. Okay? So this is basic important formula that defines what's usually called the Dirichlet convolution, but we're calling it the caret convolution because it's in a different kind of context. This is a more elementary arithmetic. The analytic number theory is actually far away. We're just talking about basic arithmetic with very fundamental things. Okay, so in the last slide here, I want to come full circle, and I want to sort of connect this with the Dirichlet series that I told you about in our first slide, coming from number theory. And it's a chance for us to sort of zoom out a little bit and think about mathematical notation. Okay. So actually, what I'm going to say now, I think is quite interesting. It's a little bit subtle. Okay. So we have these sort of two algebraic worlds that we're sort of comparing here, right? There's the Pauli number world, okay, where we have Paulis, and the operations of interest are the usual familiar ones of addition and multiplication. And let me just remind you about that, okay? So here is a Pauli, okay? 0, 0, 1, 4, 4, 4. And one way of, describing that is it's 2 times this box plus this box plus 3 times this box. And in this world, we've formally brought in this sort of notation to make things a little bit easier and also to align with the usual polynomial algebra. We said, let's define this thing here to be 1. In some sense, this is the first Pauli number, which is not a natural number, the first thing that you get when you go up one level or down one level from numbers to Pauli numbers. So we defined alpha to be this particular Pauli number, and then something like this one here, we saw that that was just the product of alpha with itself 4 times, alpha times alpha times alpha times alpha. So it was reasonable to use this sort of exponential notation that we're already familiar with to describe this thing here, right? So we had, this is like 2 times 1, or 2, just 2. This is alpha, and this is 3 times alpha to the 4. Okay, so this is the familiar sort of Pauli number language that I've used in many different situations. Let me just suggest to you a slightly different take on this. Okay, a slightly different take. So an alternative is to describe this thing here in this form, which is a little bit more verbose. To say, well, it's 2 alpha to the 0 plus 1 alpha to the 1 plus 3 alpha to the 4. Okay, where this symbol, alpha to the n, where n is a natural number, is just a symbol for the Pauli number with the single entry n. So we could imagine, talking to some people who, some students from a different culture who are not at all used to our particular notation for arithmetical operations, have never seen an exponential, for example, right? So to them, something like alpha with an n on the top right is sort of arbitrary. Sort of like if I wrote an alpha with an n on the top left, you think, well, what's that supposed to mean? Okay, but from that point of view, what we're doing here is saying, look, let's just agree that instead of using this terminology for this box, we'll use this terminology. So we're not assuming that you know what an exponential is. Okay, that's not what we're doing. We're just saying, let's just introduce this particular combination of symbols to represent this thing here. And then if they ask, well, what is alpha? Now the answer is, well, it's just a symbol. It's just a letter that we're using conveniently, sort of to give the n something to sit on. Right? From this point of view, alpha is not actually equal to this thing here. In fact, this thing here is not equal to alpha. It's equal to alpha to the 1. It's equal to alpha to the 1. And this thing here is not equal to 1. This is equal to alpha to the 0. From that point of view, these objects are all of the form alpha to the n. You have to have an exponent to bring one of these things into being. The question of what is the box alpha is meaningless. There is no box alpha from this point of view. Okay, so it's an alternative to what we're usually doing. And you can see that's in some sense a little bit more consistent because we're not treating this case and this case sort of specially. See, over here, all subsequent ones had actual exponents, but this one doesn't have an exponent, and here there's not even an alpha because we're kind of used to it, right? But in some sense, this is sort of more logical. The Babylonians would probably prefer this because we're being completely consistent right from the beginning. Okay, so having said that, let's now apply the same kind of thinking to the polystar world, where we're interested in these two operations, addition and the caret operation. Okay, so here is a polystar. It has to start with, or not start with, but it can't have any zeros. So 1, 1, 1, 2, 5, 5. Now we've seen that another way of representing this thing is with its multiplicity list. There's 3 1s, there's 1 2, there's 0 3s, there's 0 4s, and there's 2 5s. Okay. But in the same spirit as over here, here might be an alternative way of expressing, or maybe more concisely, or just an alternate way of expressing this polystar. Okay, so let's write it as 3 times 1 to the r plus 1 times 2 to the r plus 2 times 5 to the r. Now, I could also write this in vector notation. So, if I was doing it in this fashion here, this 1 to the r would really represent the vector 1, 0, 0, 0, 0. And this 2 to the r would really represent the vector 0, 1, 0, 0, 0. And this 5 to the r would really represent the vector 0, 0, 0, 0, 1. Okay? So, in some sense, these things here are just representing sort of basis vectors in this this linear world of the multiplicity lists. And so you can say, well, okay, but what is the r? What do we mean by 2 to the r? Is that an exponentiation? No, it's not an exponentiation. It's just a symbol that we've introduced exactly in parallel to this one here. But it's a symbol which naturally and pleasantly accords with our usual arithmetic, because over here, when we do the caret operation and we are multiplying two guys in here, then this exponentiation naturally fits with that. And so if you have 2 to the r times 3 to the r, you're going to get 6 to the r. You have to multiply the bases. Over here, if you have alpha to the 2 and alpha to the 3 and you're multiplying them, you have to add the 2 and the 3. Okay? Adding is sort of where the multiplication is coming from. The caret is coming from multiplying the interior objects. Now, you might say, oh, well, an alternative to this is to put is just to introduce a different symbol and sort of make a fraction and put these powers of 1, 2, 3, etc., down in the denominators. And so you could do that. So we could have also said, well, instead of writing this, let's write this. The advantage in doing either this or this is that when we want to do this caret convolution, it just ends up being ordinary multiplication in the usual sense of our familiar operations with objects like this, just using the ordinary laws of algebra. And why do number theorists want to put things in the denominator? Well, it's exactly because they're interested in convergence, like in the Riemann zeta function. They're interested in having a series so that when you actually plug in a value of s, okay, then you're going to get something which converges. For us, that's not so important because we don't believe in, the convergence or otherwise of infinite series. For us, it's actually more natural just to use this. This is a kind of a simplified version of the Dirichlet series where we're not putting things in the denominators. We don't need denominators. We can just have powers of 1 and 2 and 5, etc., as sort of symbols which represent the various multiplicities of these basis vectors. So what I'm saying here is that the usual Dirichlet series and the Dirichlet convolution or product is in some sense just an elementary and very reasonable constituent of Box arithmetic. Once we've gone from the addition and multiplication levels down to the caret operation. Okay, and we're just introducing the caret into the world of Pauli numbers and having a look at how it interacts with addition. And there's an algebra structure, and we're just describing that algebra structure. So it's in fact, very natural. It's not impossible on some other planet. They learned about this in primary school. I'm Norman Wahlberger. Thanks for listening.